Let's take a look at this circuit here. This is going to be a series RLC circuit, and we're going to have a step response for this specific case. And we're told to find V of t as well as I of t for t greater than 0. And we want to consider 3 cases, but for the sake of this example, I'm just going to consider the first case, r equals 5. Okay. And you can just imagine if you change the values of the resistances, it's going to be, you're going to pretty much compare the differences between the alpha and omega naught values, and it's going to determine whether you're going to be over-damped, critically damped, or under-damped. Okay, so I'll let that be an exercise you do on your own for the other two, but let's just do the first one together. Okay, so let's go ahead and say my value here for the resistance is going to be 5 ohms. We're given our inductor as well as the capacitance, and we're given this resistance value at the end. Okay, so at time equals 0, this connection is going to open. So we had this was connected for a long time, but at time equals 0, it's going to open, so that resistance goes away, and then you'll have an RLC circuit. Okay, so let's take a look at this. Okay, since the switch is closed for a long time, the capacitor is going to behave like an open circuit. So technically, this capacitor, so if we redraw this, if I draw the circuit again, I have a resistor. Okay, and then the inductor, I'm just going to do this here, and I'll just modify it in a second. So initially, the inductor, since it was in steady state, the inductor is going to be a short circuit, while the capacitor is going to be an open circuit. So this is short circuit and open circuit, where this is going to be 5 ohms, and this is going to be 1 ohm. Then we got 24 volts coming in here. The current we're measuring is I, and then the voltage is going to be plus or minus voltage here is what we're trying to determine. Okay, since that's the case, we can determine I naught, or our I initial value. So I of 0 is going to be I initial is going to be our 24 volts over 5 ohms plus 1 ohm. So it's going to be our 1 ohm times the 24, 5 plus 1, and that's going to give us 4 amps. Okay, and the initial voltage across the capacitor is going to be the same as that across the resistor. So this minus or plus minus voltage. Okay, and that's going to be V equals IR, so V of 0 is equal to our current, which we just said was I of 0 times R. The R in this case is 1 ohms, and an R naught is going to be 4. Okay, so we get 4 volts. So we just determined our initial current, our initial voltage. Okay, so now so this is for t less than 0. Let's look at t greater than 0. Switch is opened. So when the switch opens, we know that our I0, what we call this I0 minus and I0 plus, essentially is going to be the same because the capacitance and the inductors can't change instantaneously. So remember that from the past. But more importantly, this resistor is going to be disconnected, so we can redraw the circuit. This is our 24 volts. We have our resistor, we have our inductor, we have our capacitor. Okay, the resistor at the end is going to go away, and we're going to have, again, we're using 5 ohms, 1 Henry, 0.25 farads, and this is going to be our current I, and this is going to be our voltage V. And you see here we have a series RLC circuit. Okay, so now what we can do is, and of course it has that voltage source of 24 volts, we can now look at the characteristic roots and determine alpha and omega. So alpha is going to equal to R over 2L, so it's going to be 5 over 2 times 1, which is going to give us 2.5, and our omega is going to equal to 1 over the square root of LC, which is going to be 1 over the square root of 1 times 0.25, and that's going to give us 2. Okay, so the relationship between these two is our alpha is greater than our omega naught. Okay, so that means we are over damped for the natural response, and the total response, so this is the natural response, and then the total response is going to be V of t is going to equal to V steady state plus our transient here. Okay, so it's going to be A1 e to the minus t plus A2 e to the minus 4t. Okay, and then of course our VSS is going to be our steady state response, which is going to be our final capacitance value. So let's go ahead and this is going to be our final capacitor value. Okay, so you can consider it as being our V as we approach infinity. Okay, so V final in this case is going to be 24 volts. Okay, it's going to be 24 volts. V final is 24 volts. So we can rewrite this equation. V of t is equal to 24 plus A1 e to the minus t plus A2 e to the minus 4t. Okay, now we need to figure out A1 and A2. So we look at our initial conditions. So we look at V0. So we're going to plug in t equals 0. So we get V0 is, we said was 4, is equal to 24 plus A1 plus A2, or minus 20 is equal to A1 plus A2. And we know that the current cannot change abruptly across the inductor, and it's the same thing through the capacitor. So at t equals 0 plus, we have the inductor and then the capacitor in series. So we can say I of 0 is equal to C dV 0 over dt, which is 4, and then we can rewrite this and say dV of 0 over dt is equal to 4 over C, and our capacitance value is 0.25. That's going to give us 16. Okay, now we got 16 here, and we can use this condition and now take the derivative of V. And if we say dV dt, so we take the derivative of this guy, So we get dv dt is equal to minus a1 e to the minus t minus 4a2 e to the minus 4t, and then at t equals 0 we get dv 0 over dt, which is said was 16, is going to be 16 equals minus a1 minus 4a2. Okay, and now we can solve for a1 and a2, and what we get, we can get a1 is equal to minus 64 over 3, and a2 is 4 over 3. We plug that back into the equation up here in green, and we get v of t, our response there, is 24 plus 4 over 3 minus 16 e to the minus t plus e to the minus 4t. Okay, and that's going to be our voltage response. Highlight that. Again, since our inductor and capacitor are in series for t greater than 0, the inductor current is going to be same as the capacitor current, so IT is going to equal to C dV dt. Okay, and then we can rearrange this. We get IT is equal to 4 over 3 4 e to the minus t minus e to the minus 4t. Okay, and that's going to be our current as a function of time. If you wanted to test this, you could say I of 0, and if we plug in I of 0 for time t here, we get 4 amps as we expected above. I of 0 we said was 4 amps here. Okay, and that's how you would do this problem for the resistance value of 5 ohms. We could, and I want you to repeat this for the other two values and see how to solve that problem. Okay, and then again, this is a step response of a series RLC circuit.